All right, so in chapter 5, we looked at designating R or S to stereocenters of tetrahedral carbons. So stereocenters have to have 4 unique substituents coming off. We have something similar with alkenes, though, but there's a slightly different naming convention. So let's compare these two alkenes. How are they related? Are they the same compounds? Ah. They have the same connectivity. Are they mirror images? No, they are not mirror images. So what would they be? Diastereomers. All right. So just like if you were to take a nutrition class, you would learn that trans fats are really bad for you. Cis fats are the natural fats. They're the ones that don't cause as many problems. So these are diastereomers. They have very different physical properties. All right, if we think about the one on the left, what would you call it? Cis or trans? Cis. So you could call this one cis if you wanted to. And this one trans. That's one easy way of distinguishing alkenes, is whether or not you've got identical groups on the same face or opposite faces and designating them as cis or trans. However, we will run into some situations where that's simply not good enough. Let me just close this and restart it. It's going to bug me. All right, so let's look at another example. All right, so for this example, I'm still going to have an alkene, a carbon-carbon double bond, but I've got a fluorine, bromine, hydrogen, and chlorine coming off, versus this one. What's the relationship between these two compounds? How are they related to one another? Yeah, they're not mirror images. Same connectivity, but not mirror images. So same idea. These are diastereomers. They have very different physical properties from one another, meaning different net dipoles, different boiling points, different melting points, things like that. All right, can we designate these as cis or trans? No, we can't. We don't have identical groups to compare in any way, shape, or form. So we have to have a different naming system for these. So I'll show you what's commonly done. First thing I always do is I imagine cutting this double bond in half. So draw kind of a dotted line going through that double bond. And then I would focus on this side of that double bond. What would be higher priority, fluorine or bromine? Bromine. It's much heavier, right? So I put this as priority 1 off of that carbon coming off the alkene, and this would be priority 2. Okay, and then over on this side, I'd say for this carbon, what's the higher priority? Chlorine. So that would be priority 1, and the hydrogen would be priority 2. All right, if we do the same thing on the other side, though, we could say on this side, what's higher priority? Well, we already said bromine, so label that priority 1, fluorine priority 2. And then on this side, the chlorine, still priority 1, but now it's on top. Hydrogen's priority 2, and now it's on bottom. All right, so let's take a look at this one down here. Let me change pen colors. If we look at this one, the highest priorities are on the same side. Meaning the same face of the double bond. Over here, if we look at it, they're on opposite sides. We don't like to use cis or trans in this situation because we're not comparing identical substituents. So instead, we use a completely different naming convention. If we look at the one on the left, if they're on the same side, these are called Z alkenes. So if we were to name this, we would start the naming system with a Z in the very front to indicate that the highest priority substituents coming off that alkene are coming off the same side. All right, the other one is an E alkene. All right, this does confuse people, and I've got a cheesy way of remembering this. I remember Z as the same side. You can say it with the French accent if that helps. But in a weird way, that's what I used to remember it when I took OChem, and it's stuck with me through my grad school and even through the past 5 years of teaching. So Z same side is a Z alkene. E is Enthagen. It's a German word meaning opposite. So if you know German, you can use that. But choose whatever works. Does that make sense? We're going to come back and talk about alkenes later. They just kind of throw it in this chapter to explain why they're diastereomers and how to differentiate different versions of alkenes, because they're very different from one another. All right, the other kind of odd thing that they throw into this chapter is something called a Fischer projection. Yeah, that was a good question. We haven't really done naming of alkenes. It's pretty simple, though. It's almost identical to alkanes. What do you think the difference might be besides the Z and E prefix? Change your suffix to E-N-E. It's as simple as that. And then you also need to number showing where the double bond starts at, but we'll go over that when we hit alkenes. Yeah. All right, so let's do Fischer projections really quick. This is also kind of an odd thing that they threw into this chapter, but it's loosely related to stereochemistry. And it's kind of a shortcut for showing stereocenters. So Emil Fischer was the chemist that helped devise this system. He worked with a lot of complicated carbohydrates that have a huge number of stereocenters on them. He found it to be really time-consuming and tedious, so he came up with this shortcut. And the shortcut's pretty easy to remember. The first one is that all horizontal lines are assumed wedges. However, you just draw them as a straight line. You don't include the actual wedge. Does that make sense? All vertical lines are dashes. So this made it a lot easier for him to write out super complicated carbohydrates without having to fill his paper with dashes and wedges. So I'll show you an example of this in context. So the first one, we'll just do a simple one. And anytime he worked on these, he didn't worry about bond angles. He just showed them as crosses, essentially. So he had an ethyl group sticking up off the top, a methyl group on the bottom, a hydrogen, and an alcohol. Let's redraw this using a bond line view. So if we think about our horizontal lines going left and right, those are assumed wedges. So it kind of looks like a bow tie coming off here. And we've got a hydrogen on the right, and alcohol on the left. And then vertically, we know we've got dashes. And we've got an ethyl group sticking up top and a methyl group sticking down below. Does that make sense? So the vertical portion, think of it as being curved away from you. The horizontal portion is coming towards you. I'll show you another cheesy example from that Master Organic Chemistry website. It's the cat view. All right, so if you think of a cat laying on its back, you've got a head sticking straight up, a tail down below, a foot, a foot, a foot, and a foot. So if your cat's laying on its back, all feet are sticking out towards you, the head's kind of curled back and the tail's curved back. That's the same idea, right? So if we were to redraw this one, we would say, all right, each one of these feet is an assumed wedge kind of poking out at you in space. Those aren't the cleanest looking wedges, but you get the idea. The head is kind of curved back and the tail is curved back. So that backbone of the cat is curved back and away from you. The feet are pointed out towards you. Does that make sense? Yeah, the cat is very flexible. We'll say that. Oh yeah, that should be a T on the bottom. Unless the cat grew a new foot. All right, so this is the cat tummy view. Oh, there we go. All right, let's do another example, and I want you to help me find stereochemistry on this next one. We're not going to use this very much until we get back into carbohydrates, but there may be some problems on sapling where you need this. So this one, we've got two crosses, hydrogen here, alcohol here, chlorine here, hydrogen here, and alcohol there. So we have two different stereocenters. We've got one up here in red, other one down on the bottom in green. Let's determine the stereochemistry for each of those. So let's do this as a class, and I'll try to walk you through it. Let's do the red one first. What's the highest priority going to be? Bromine. All right, followed by the oxygen, followed by the carbon underneath, right? So I just put 3 down here. So if we go ahead and we do this, it looks like we're going to the left, which is normally an S. Are we going to stick with an S? No, why not? The hydrogen's an assumed wedge, right? So if we look at this one, this is an R stereocenter because that assumed hydrogen going horizontal is a wedge, right? We're not showing it as a wedge, but it's assumed to be one. All right, let's do the same thing with the next one. So green down here, chlorine would be the highest, followed by our oxygen, followed by the carbon up here. So if we go like that, it looks like it's an S going to the left. However, the hydrogen that's horizontal is an assumed wedge, so we've got to flip it to an R, right? So I'll erase this, and we'll indicate that this one is an R. Does that make sense? Like I said, it kind of bugs me that he throws this in kind of willy-nilly into this chapter, but it's important for understanding stereochemistry when we get into carbohydrates in third term organic. So we'll go back third term organic chemistry and review some of this stuff a bit more.